Here we're going to talk about Newton's second law, but first we'll review the concepts of forces and free body diagrams a little bit. Try this one. A book sliding rightward across a level table. Draw the free body diagram for the book. Here's our book. We have the force of gravity acting down on the book. We have the normal force acting upward on the book. And if the book is sliding rightward across the table, then we would have the force of kinetic friction to the left. We're not told that the book is being pushed or pulled by any other applied force, so that's it, just the three forces. So in this case, the book is moving to the right, but it must be slowing down because the net force is to the left. So we have an unbalanced force to the left. So no applied force. So we know about Newton's first law of motion and inertia. Here we're going to look at Newton's second law of motion. So now that we know about Newton's first law and inertia, we'll look at Newton's second law. And here Newton discovered two relationships. One is the relationship between the net force acting on an object and the object's acceleration. The other relationship is between the object's mass and its acceleration. Once he found those relationships, he combined them. That's what we're going to look at here. So if the net force acting on an object is not zero, then the object will be accelerating, and it will be accelerated in the same direction as that net force. So Newton found that, as this statement says, the acceleration of an object is directly proportional to the net force acting on the object. That's how we would write that. Acceleration is directly proportional to the net force on the object. So if I double the net force on the object, then that means I have to double the acceleration of the object. If I triple the net force, then I triple the acceleration. That's what that direct relationship means. The other thing we see in Newton's equation for his second law is that acceleration is inversely proportional to the mass of the object, which we can write like this, because we can see that the mass is in the denominator. That tells us that as mass increases, the acceleration decreases. So if I double the mass of the object, then the acceleration will be cut in half. So the more mass of the object, the harder it is to change its motion. That relates back to Newton's first law because, remember, we said that objects with greater mass have more inertia. This is a very common way to write Newton's second law equation as well. All we've done is rearranged the equation that we wrote down earlier. So net force is equal to mass times acceleration. We can use this formula to find an object's weight as well. You recall that the weight of an object is the force of gravity exerted on an object by a planet or a moon or some other large body. So if the acceleration, A, is 9.8 meters per second squared, then we can rewrite the equation from Newton's second law like this, where Fg is the force of gravity, or the weight of an object, m is the mass of the object in kilograms, and g is 9.8 meters per second squared, which we call gravitational field strength. Or we could write that as 9.8 newtons per kilogram, because newtons per kilogram are equivalent units to meters per second squared. So Fg is the weight of the object, m is the mass of the object, and those two things are different. They often get confused, but we should be careful not to confuse them. Weight is measured in newtons because weight is a force, the force of gravity. The direction of that force is always down. Later on, we'll see that the direction of your weight is actually towards the center of the Earth. But from a practical point of view, for us, that just means that it points straight down. Let's try an example. Weightlifter lifts a 160 kilogram weight by exerting a force of 1.8 kilonewtons up. The force of gravity on the object is 1.6 kilonewtons down. Draw a free body diagram for the weight. Then we're going to find the net force on the weight. And once we have the net force, we're going to find the acceleration of the weight. So here's our free body diagram. We have our upward force applied by the weightlifter, and we have the downward force of gravity. So the net force, when we add them together, taking up to be positive and down to be negative, we have 1.8 kilonewtons minus 1.6 kilonewtons, so we get 0.2 kilonewtons up, because our result is positive. Now to find the acceleration of the weight, we'll write down our given values and our unknown, like so. We know the mass, we know the net force, and our unknown is the acceleration. Notice that we're converting the force to newtons, and that's because we're using kilograms for mass, and we expect to get meters per second squared for the units for acceleration. In order to do that, the force has to be in newtons. So we'll use the equation for Newton's second law, and then we'll substitute in. So we've got our force, 200 newtons, the mass, 160 kilograms, and we get an acceleration of 1.25 meters per second squared. Because we got a positive result here, that tells us that the acceleration is up. So our final answer, the acceleration of the weight is 1.2 meters per second squared up. Let's try one that involves the equations of motion. Here we have our car traveling at 25 meters per second forward, and the driver slams on the brakes and stops in 3 seconds. Calculate the acceleration of the car and the net force needed to cause that acceleration if the mass of the car is 1,200 kilograms. So we'll write down our given values first. We've got v1, our initial velocity, 25 meters per second. We'll take forward to be positive. v2 is 0 because the car is going to stop. So that tells us that v2 is 0. Time is given as well, and our unknown is the acceleration. So far. If we use our acceleration equation from the 5 equations of motion, we can substitute the values in that we have, and we get an acceleration of negative 8.33 meters per second squared. Keep that in mind, because remember that Newton's second law tells us that net force has to have the same direction as acceleration. So our acceleration is 8.3 meters per second backwards. That's what the negative means. In this case, it means that it's backwards. Of course, that makes sense because the car is slowing down. Now to calculate the net force needed to cause the acceleration, we know the mass of the car, and we have our acceleration now, so we'll use those as given values. Our unknown is the net force. So we'll use Newton's second law arranged this way to get F net by itself rather. So we substitute in the value for mass and our acceleration, and again we get a negative value when we work that out, which tells us that the net force is also backwards. In this case, 10,000 newtons backwards. That's a pretty big force. That's approximately equivalent to lifting up a bag with 10,000 apples in it. Well, that makes sense. If you're going to stop a car, you need a lot of force. All right, now we're going to try a simulation, a computer simulation, and a few questions to try for some practice.